So the next type of reactions we're going to take a look at are called decomposition reactions. And you can kind of think of these as the opposite of synthesis reactions. So typically in synthesis reactions, we're putting things together to make a single product. In decomposition reactions, we're taking things apart into smaller pieces. Most of the time you're talking about a binary compound decomposing into its elements. But that's not the only kind of decomposition reaction. Sometimes we have a more complex compound decomposing into smaller pieces, smaller compounds. And I'm going to give you an example of one of those in just a little bit. Okay. As you're doing this, though, you want to make sure you're careful that when one of the elements that you're producing is one of the diatomics, that you're very aware that it should be O2, N2, Cl2, etc. That's one of the most common mistakes at this point, is separating something that contains a halogen, for example, into its elements and forgetting that you need to make that element diatomic, regardless of what it says on the left of your reaction, right? So just be careful of that. So we're going to take a look at 4 different examples. The decomposition of potassium bromide, decomposition of lead-4 nitride, catalytic, and we're going to talk about what catalytic means, catalytic decomposition of dinitrogen monoxide, and finally the decomposition of aluminum carbonate. The first three of these are simply binary compounds splitting into their elements. Super simple. The fourth one is a special kind of decomposition reaction that we're going to study in the class, the thermal decomposition of a carbonate salt. And that doesn't break up into elements. It breaks up into smaller molecules or smaller compounds. So we'll take a look at that. Okay, so looking at the examples, the first example that we had was the decomposition of potassium bromide. So potassium bromide is KBr. That's a solid. Ionic compounds, unless they're dissolved in water, are always solids at room temperature. Okay. Simple decomposition is just a binary compound decomposing into its elements. So KBr is made of potassium, which is a metal, and bromine. Bromine is one of the 7 diatomics. So it needs a 2 here. And according to the periodic table, if you look, you'll see that bromine is in fact a liquid at room temperature. So then to balance this, I simply have to put a 2 in front of the KBr and a 2 in front of the K. And now we've got a balanced chemical equation for that decomposition. Okay. Similarly, if I were to do lead-4 nitride, lead-4 is +4, nitride is -3. So lead-4 nitride would be Pb3 and 4, another ionic compound, so solid at room temperature. And that's going to break up into lead, Pb, and nitrogen, which is N2. It's another diatomic. That's a gas at room temperature. So I'd need to put a 2 in front of the N2 to get 4 of those, and then a 3 in front of the Pb, and you're all set there. Now, the third one says catalytic decomposition of dinitrogen monoxide. So dinitrogen monoxide is N2O, and that's a gas at room temperature. Okay. So the decomposition is pretty easy. If it's a binary compound, it's just going to split up into its elements. So N2 and O2. And I can balance that as usual. I'll need to put a 2 and a 2 to balance it. But what does catalytic mean? So catalytic means we're dealing with something called a catalyst. So a catalyst is something that speeds up a chemical reaction, but isn't consumed in the process. The catalyst for this reaction is a cobalt-3 oxide powder. And the way we indicate that there's a catalyst involved is we write the formula for the catalyst or symbol for it above the arrow. So cobalt-3 oxide is CO2O3, and that goes above the arrow showing that this decomposition happens, but it requires an additional substance to speed it up to make it actually work in real time. So catalysts speed up a reaction, are not consumed in the reaction. And then the final example that we were talking about is the thermal decomposition of aluminum carbonate. So aluminum carbonate, Al2 parentheses CO3, 3, another ionic compound. Okay.
Thermal decomposition means it requires heat. And the way I indicate that it requires heat is I put a little triangle above the arrow. That means heat is required for this to happen. Carbonates, when you heat them, release carbon dioxide. And what they leave behind is the oxide of the metal that you're heating. So aluminum carbonate, any metal carbonate, when heated, releases carbon dioxide gas into the atmosphere. And what's left behind is the oxide of that metal. So aluminum carbonate then produces aluminum oxide, Al2O3, which is a solid powder. So this is solid. So it's going to actually look the same here. This is a white solid. This is a white solid. You're not going to really tell, except for the fact that it's going to get lighter. The mass is going to go down because I'm releasing into the atmosphere some of those atoms, the carbon dioxide gas. Okay? It requires heat, so it's got a triangle over the arrow. So I just need to go ahead and balance this, right? So if I look at, I've got two aluminums, that seems to be fine. There aren't any polyatomic ions that show up on both sides, so I can't do that. Non-metals, I've got a total of 3 carbon here and 1 carbon here. So if I put a 3 in front of the CO2, there's my 3 carbons. And now it's the oxygen's turn. This is 3 times 3, or 9 on this side. This is 3 and 6, that's 9 on this side. So that is the balanced equation for that decomposition. And that's really all there is to it. You're going to see carbonates. Those are a special class of decompositions. And then there are some other ones that are going to crop up in our labs and such that are special decompositions that don't decompose into elements necessarily, but into smaller pieces. But we'll encounter those as we go, and we'll talk about them when we get there.